In this class 3 review class, we got a couple of threads that we could follow. So we've been doing obviously the integration stack preparation, which I believe everyone should be finished by now. We have the unit 1 and 2 exponentials logarithm stuff, which we might have a look at depending on attendance today. But the other thing you were interested in was having a look at probability stuff. So update me on that. Are you still looking at discrete binomial or? Hello?
What?
Did you hear what I was saying?
Um, there's music playing on my PC, but I can't pinpoint where it's coming from.
Yeah, sure.
I'm just closing
Okay.
random stuff to see if that fixes it.
Gotcha. But yeah, I was basically just outlining the threads we had. We had the
Oh, yeah. Yep.
Unit 3-4 stuff, which was the integration stack. I'm pretty sure everyone's finished that, more or less finished that by now. There's the Unit 1 and 2 stuff for the exponentials logarithms, and there was your recommendation of the probability stuff. Just getting a pulse check. Is there any stuff that people specifically wanted to have a look at, or? Because I'm prepared to do either, maybe even split the class 50-50. Because I think, Benedict, are you doing, I think, if I remember correctly, integration stack still coming up?
Yeah.
Yeah, you're still doing integration stuff. How are you doing with that? Are there any questions in particular you wanted to focus on?
No, there's no questions.
No questions?
Probably I'll have questions. But
Say again, sorry?
by next week, I'll have more questions
Oh,
to.
yeah, sick. So yeah, if you have anything specific, then let me know. We can definitely dedicate class time to it. But for now, this will be beneficial to both of you anyway, which will be looking at the probability stuff ahead of time. So let's crack on with discrete. There is a chapter technically beforehand which covers a bit of the probability fundamentals. It's not actually a separate chapter, sorry, it's 13a, where it covers some of the really fundamental stuff, just like, hey, if you want to find the probability of a thing occurring, count the number of events where it occurs and divide it by the total number of possible events. Right? If you have a six-sided die, you might roll a 6, there's one chance of it happening out of a total of 6 possible outcomes. I feel like we probably don't need to revise any of that sort of fundamental stuff there, so we'll crack on straight with discrete here, and if there are any lacking of fundamentals there, I'll explore that during this chapter section here. Starting out with discrete. So what does discrete probability mean? Well, discrete probability you can think of as a subset of global probability, where it concerns itself primarily, or exclusively rather, with quantities that only occur in very specific outcomes. The six-sided dice example from before, right? You can't roll a 1.5 on a six-sided die. You only have the numbers 1 through 6. This makes it discrete. The lines tend to blur a little bit with continuous and discrete because on a technical level, if we think about like a physics perspective of continuous versus discrete, we are actually limited by our own measurement capabilities, right? Continuous quantities are those that continue on to infinite decimal places, but in the real world we are limited by our own ability to measure such things. And so by definition a continuous quantity is something that is pretty much only cut off short simply because we either can't be bothered going through more decimal places to measure it properly, or we lack the physical ability to do so. Continuous is going to infinite number of decimal places, your measurements usually, whereas discrete you only have certain particular outcomes. The way you will often see discrete probability questions represented is with a probability distribution table. So here's how it works. On the top you have x and all of the possible values of that little x. Little x you can think of as the possible outcomes for your experiment. So imagine this is a impossible three-sided die. You have the outcomes 0, 1, 2, and 3. On the bottom are the probabilities of each of those things occurring, and you have the general notation probability capital capital X is equal to little x, which is why you see little x being 0 here, this is equal to 0. Little x being 1 here, this is equal to 1. Capital X is referred to as the discrete random variable that explores the scenario that you're trying to do here. So in this mock example that I gave, a possible three-sided die, capital X would be the discrete random variable that explores the outcomes of that three-sided die. Well, I guess this would be four-sided actually. This would be a D4 that has a 0 on it. My mistake. It'd have the outcomes 0, 1, 2, and 3. Yeah, it's a bit tricky. Sometimes you can get a bit misled by what a 0 actually means on this. It doesn't mean like a 0 probability. It means a specific outcome. You can roll a 0. And D4s do exist in the real world. Okay. The other thing about probability distribution tables is that they must conform to all the regular, normal probability rules. The main ones of note here are going to be that all probabilities in a scenario need to be between 0 and 1, 0 being 0%, 1 being 100%. You will never have a number that will be outside of those boundaries. The other thing is that the sum of all probabilities in the table needs to add up to 1, and that's simply to validate the fact that your table does in fact include all possible outcomes. Right? If you explore all possible outcomes of a given scenario and they don't add up to 100%, then something's a bit off, because either you've calculated the probabilities wrong or you've excluded a scenario. Right? Even if that scenario, well, I'm thinking about the hypothetical where you have a scenario that has a 0% likelihood of occurring. If it has a 0% likelihood of occurring, it just shouldn't exist in the table, because 0% likelihood means an impossibility. So just not a scenario worth putting on your table. And lastly, the thing you'll find pretty helpful for these kinds of questions that involve probability tables is to use complement probabilities. So just a bit on notation here. Probability A and probability A not. That dash there basically just means everything that is not A. So let's say on a coin toss, for instance, you got heads or tails. If heads was probability of A, then tails would be probability of A not, A dash, because you've got the probability of a head and then the probability of not a head, which in this case would be a tail. If we use an example that has more than one or more than two possible outcomes, you would have maybe probability x equals 0 as your probability A, and therefore probability A dash would be the addition of all of these three. Probability x equals 1, 2, and 3, because everything that's not what you started with. We'll pause there for a bit. Any questions about anything I've covered so far? Alrighty. Next up, how do we actually start doing these tables? How do we fill them out ourselves? We're going to use an example. Suppose a jar contains 4 white and 6 black balls. If 3 balls are drawn at random with replacement, that's going to be a term you see quite a bit, a key important term there. Express the probability distribution of selecting a white ball using the probability distribution table. So, again, this is what our probability distribution table looks like, just generically speaking. And if we think about what the scenario actually is, there are 3 balls that are being drawn at random with replacement, and the thing that we are tracking is the number of white balls that are selected. So when you do your capital X, that would be defined as the possible number of white balls. So all of these outcomes up here are tracking white balls drawn, not black balls drawn. It's an important distinction to make. So as far as the key terms that are relevant here, this bit is kind of self-explanatory. This key term here, with replacement, means that every time you are drawing a ball from this jar, essentially it is like on iteration 1, you draw a ball, you look at it, you note the color down, and you put it back in the jar, shuffle it up. Then on iteration 2, when you're drawing the next ball, it's already been shuffled, it is basically back to the exact same state that it started with. So the probabilities are not going to be changing. Balls are not exiting the jar for longer than a single iteration. That's what with replacement means. And the last key thing you need to watch out for, as I highlighted already, was what your distribution table is actually about. There are two things that could be tracked here. We're told to track white balls, not black balls. Very important because the number of white is different to the number of black. If you accidentally track black balls, you have got a valid probability table, but an incorrect answer. So when it comes to setting up the upper row of our probability distribution table, we need to think about the scenario. Okay, there's 3 balls being drawn at random, and they're being put back. So if we think about the number of possible white balls that could be drawn, you could go 3 times in a row and not get any white balls. Or you could get 1, or you could get 2, or you could get a maximum of 3. That's why we are limited between 0 and 3 for our that upper row there, the number of outcomes. How do we now calculate them? Well, luckily with replacement, the calculation of such things is actually quite trivial, because you essentially just want to know what the probability of drawing a black ball is and compare it to the probability of drawing a white ball. There's 4 white, 6 black, which is why 4 and 6 out of 10 respectively are going to go to your probabilities. From here, we're just going to calculate each individual one. And because these are done in sequence, right, you are drawing one ball, noting it, drawing another one, noting it, drawing another one, noting it. Any probabilities with scenarios done in a sequence multiply across that sequence. So drawing no white balls effectively means you drew 6 black. You drew 3 black balls, and so it would be the probability of 6 out of 10 repeated over and over again until you multiply through and simplify. The reason this won't be decrementing is because every time you draw one, you're putting it back. It remains 6 out of 10. Simplify down, and depending on if you've got CAS or not, you'll be giving it as a decimal or otherwise, depending on what the question is asking for. X equals 1 gets a little bit trickier because you now have to consider the order in which these balls are being drawn. You could draw the white ball first, you could draw it second, or you could draw it third. Because these are mutually exclusive events, you cannot in one scenario get both this and that, and furthermore also this. You can only have one outcome by the end of any given trial, any iteration of this. And because these are referred to as mutually exclusive events, you calculate them individually and separate them by an addition sign. This is stuff that gets covered in much more detail in the counting methods section, the difference between when you add probabilities together and when you multiply. Multiplication is done when there is a sequence, when you have step 1, step 2, step 3. Addition is done when you want to essentially look at multiple parallel sequences that could not occur at the same time, but are thus still likely, or thus still possibilities. Yeah, Nihal?
So is it like if we can order 3 things from a restaurant and we have like an appetizer, a main course, and a dessert?
Yep.
And from each we can choose 3 items.
Yep.
One of 3 items. So will the addition be the finding what we choose in each section, or is it like the total thing?
Yeah, so it depends on the question that's actually being asked here. I know the question, I'm pretty sure the one you're specifically referring to is one where you're counting the number of possible choices. The rules are going to be different depending on if you're counting possible choices versus the probabilities. I'll give an example, which is if you want to count the number of possible meals you can have, let's just go with your 3, I think you said 3, 3, 3 for each, just to make it easy. You essentially have 3 possible choices for your entree. And so because those are mutually exclusive, you can't have 2 entrees in this scenario, or 3 entrees in this scenario, those are all going to add together to give you 3 possible choices for that stage. But you then move on to your main meal, right? In this hypothetical, you have to pick an entree and a main. That is done in a sequence. You get your entree first, then you get your main. Let's say there's, again, 3 possible choices there. Within that particular stage, you can only have one option within there, again, hypothetically. And so because, again, you can only have one of the three options, those three numbers add up together, the three choices, 1, 2, and 3, add up, giving you a further three choices for that stage. Same logic applies then for the dessert bit. And so once you have your individual number of choices across each stage, you then multiply those numbers across. So 3 times 3 times 3, 3 cubed, 27, number of choices there. That's from like a choices perspective. If you do something similar to this, the lines get a bit harder to, let me see, how can I explain it a bit better? If you're then dealing with like probabilities of certain outcomes occurring, like let's say you want to find the probability of a certain entree, or a certain main meal, let's say, I don't know, a steak was one of your main meals. You want to find the probability of getting a steak, plural, or just period. You now want to find all of the individual sequences that contain steak and exclude the ones that don't. So you've got your three possible outcomes at the beginning for your entree. None of those matter because all you're looking for is the steak.
So is it a combination thing?
Yeah, so you could do that in a combination sequence of being like, okay, you have entree 1, main steak, and dessert 1. Or you have entree 2, main steak, dessert 3, and you can multiply all those together individually, but add each individual stream. Actually, do I have a... Let me see if I've got a tree diagram. Should make it a little bit easier to explore. Probability, probably in the fundamentals, multi-stage experiments. So it would be something like this, where you choose entree 1, and because you've chosen entree 1, all of these are now barred to you. You now want to only look at your mains outcome. Let's say your main that you wanted was option 3. You basically blind yourself to all of these and then continue on once again to see what's left over. And you simply just go down each individual line, multiply along the full line, but add the number of lines that contain, in this hypothetical, option 3. There are ways to simplify that further, I'll be honest, but just to highlight the distinction between when you add and when you multiply, the best way to visualize it is with a tree diagram here. This is a multi-stage experiment. You multiply along the branches, and if you want to consider multiple possible sequences, you just add any other individual branch sequence to it. So for instance, the branch sequence 1 and 3 multiplies, the branch sequence 2 to 5 multiplies, but if you want to consider both in your probability, you then add the final results of those multiplications together.
Yeah, I think I got it then.
Yeah, cool. Awesome. And we're seeing a bit of an example of that here on a short term, right? You've got the white being chosen at the very beginning, maybe in the middle, maybe at the last. You have to consider the number of ways it could be chosen. Same thing with the x equals 2, x equals 3. Just remember that you're tracking the number of white balls, not black balls. So x equals 2 is not the same as x equals 1. Now you have 2 whites, 1 black, rather than 1 white, 2 black. And because these are different probabilities individually, although the logic is the same, the probabilities you're using in the sequence are therefore different. And then just to quickly check your result, just make sure everything in there adds up to 1. And you might also do a bit of another sanity check as well, being like, okay, well, if I think about the real probability of getting 3 white balls in a row, that should be a small number. Or if I think about the probability of getting any one of these outcomes, it should make at least a little bit of sense at a glance. So do a bit of a sanity check there. If this ends up being your biggest probability and the others end up being smaller, you might want to double check your math. But the main one's going to be making sure everything adds up to 1, right? If everything adds up to 1, then the likelihood you did it correctly is pretty damn high. In fact, likelihood might be just 1. Cool. Next up, we kind of briefly touched on this already, which was this idea of finding and summing up probabilities in a sequence. The way that works on a probability table is as follows. Let's see this example. Find the probability x is greater than or equal to 2. pay close attention to the use of sign here. This inclusive of 2 means we include that value. If it was just greater than 2, you would only include the last option of 3. The thing that is greater than or equal to is the outcome, not the probability. And so the way it works on a probability table is, again, just the addition, right? And this just goes back to what we were discussing earlier, which is these are each themselves mutually exclusive. You cannot both get 1 white ball and 2 white balls at the same time. These are mutually exclusive events, which is why the calculation of these was done multiplicatively, but to find the probability of getting either of these outcomes, it is additive. You add together. Next up, let's say you get a scenario like this. It's unlikely as an example, as an actual real question, but it's just here to highlight a technique that you can use, which is we're told to find the probability of x being greater than or equal to 1, and we're like, cool, okay, x greater than or equal to 1 is all of these outcomes. Unfortunately, they are all unknown. What are we going to do here? Well, this is a use of complement probabilities. Because we know this one, and because this one is the only, said otherwise, because this and these should therefore add up to give 1, because this is just x equals 0, and this is everything that's not x equals 0. This is the full rest of the table. We can find the rest of those outcomes, or at least the addition of them, by doing complement probabilities. So if this plus all of this equals 1, then you can rearrange that to say 1 minus this gives you all of that. Therefore 0.7. Now you're not going to find these individual outcomes from this, but unless there's further information, of course, but you can at least get the sum of what these would all be. And you use this a lot in the next section, which is binomial probabilities. You use this in, yeah, I won't even, we'll get there when we get there. But it's one worth highlighting for sure. Before we get into this nasty looking thing, were there any questions about any of this so far? Alright, so this looks like hell. What is actually going on here? The question it's asking you here isn't even necessarily finding a probability. What they're asking you to do here is find the possible values of p. So we look at our probability table and we're like, cool, okay, p is in all of these outcomes, or these probabilities here. So what do we do from here? Because every probability in a table needs to add up to 1, we can start by getting our equation. Whenever you're trying to find a variable, one of the things you're trying to do is figure out how you create an equation that has just that variable in it. Because if you have just the variable, you can then solve for that variable. The one that matters quite a bit for these probability tables is that everything needs to add up to 1. So you grab all these probabilities, make them add up to 1, and then simplify whatever you've got. This is now a quadratic, which you can feel free to solve however you wish. I've done a quadratic formula approach, but a factorization approach could also work perfectly fine as well. From here you do get 2 possible outcomes here. P equals 1/5 and P equals -1. One of those is only one of those is valid. And that's going to be the P equals 1/5. The reason why isn't, it's fairly obvious, but not super straightforward. Worth highlighting, P is not actually a probability in this question. It's a coefficient that multiplies up into a probability. So it's worth highlighting that, because if P was squared, for instance, then the fact that it's a negative doesn't necessarily make it invalid. If we had P squared, if this was -0.5 and you had P squared, you'd have -0.5 squared getting you back to positive 0.25. Suddenly that's valid. So you might have strange questions where P or the outcome you have might be negative, but that might not necessarily be a immediate issue. Yeah, Taihan?
Yeah, I just want to so yeah, basically this question isn't really that related to probability. It's basically just like a substitute solved type thing. And then the reason that the P-1 doesn't work is that if you subbed it into the -1 column, it just give you negative 0.5, which
Yep.
doesn't work, right?
Yeah, there's a lot of reasons why this one won't work. Subbing in there makes it negative. Subbing in here makes it both negative and bigger than 1.
Yeah.
Yeah.
And there's no scenario you'd have where values from the probability table would be negative and still adding up to 1. That's just not possible.
Correct, yeah. Negative probabilities are blacklisted entirely. So even if it did somehow add up to 1 still, which might be a weird question that comes up, you still blacklist it because it's not valid to have probabilities negative. But yeah, again, the thing I want to quickly reiterate here, I haven't seen it happen before, but it's technically possible. You might have a bunch of squared numbers in here, and the p-value being negative might not be an issue. I just want to re-highlight that p isn't a probability, it's using calculating the probability here. So if all these calculations turned out to be good, then this would be valid. It does not, so it's not. Okay. Next up is conditional probabilities. So depending on how long it's been for some of you, we might need a refresher on conditional probability. So let's discuss that. This notation here with the pipe symbol there, the same way you define like a domain on a CAS, for instance, that symbol there denotes a conditional probability. It's a special kind of subset of probability. In fact, what I'll do is even further, I'll pull up the entire conditional probability notes here because it's worth really understanding what the hell conditional probability even is. So before we get into the notation of it, let's try to understand what it actually is. Conditional probability at its core effectively is just restricting the number of possible events that you look at. So if we use a Venn diagram to describe the number that's rolled on a 6-sided dice, the question that's being asked is find the probability of rolling a number greater than 3 given that we rolled an even number. So that key phrase there, given that, is pretty much a dead giveaway that you're dealing with conditional probability. That key phrase, given that, essentially says, hey, I know that there's 6 outcomes for a 6-sided die. Sure. I'm telling you to ignore that and assume that the number that was rolled was an even and use that as your new total. So what this would look like on a Venn diagram is to say, okay, well, the numbers that are greater than 3 are going to be 4, 5, and 6. The numbers that are even are 2, 4, and 6. And the numbers that are neither are going to be excluded. Because we are now saying an even number was rolled, we're going to ignore all of this stuff and just focus on this even circle here. All the outcomes that are even becomes your new total. You no longer include these in your total number of outcomes. That's what conditional probability is. Quick questions. That's why odd numbers just aren't considered. It basically makes a new domain for the... Yes, absolutely. It makes a new domain for the data that you are looking at. It excludes anything that is no longer in this conditional. It's saying, hey, I know that there's more outcomes, ignore them. That's what it's saying to do. Yeah, spot on. Okay, so what that would look like in this example, for instance, probability of rolling a number greater than 3 given even. Well, since we're now looking at this, there's only 2 numbers that are greater than 3 out of a total of 3 possible outcomes. Again, we're only looking in this subset. So that's going to give us a 2/3 outcome rather than a 3 out of 6, which would be if you did not have the conditional applied. It's worth really pointing out that that's what's fundamentally happening, because I think it makes it easier to understand why this probability is, why this formula is the way it is. So again, the notation here. Probability of A given that B has occurred. You can basically assume this pipe symbol means given that. So in this case, it's the probability of rolling a 3 given that we rolled an even number. That's how you read that. The equation for it is you want to find the intersection of those two events, rolling a 3, a greater than 3, and even. And you want to divide by the probability of the conditional even. What does that look like? Well, if we consider what we just did here, for the number of possible outcomes, we found that the numbers greater than 3 were exclusively found in the intersection section. Right, this is the intersection of the two Venn diagram circles. That's what this is, our numerator of 2. Probability of B is the probability of the conditional. That's this bit, of which there were 1, 2, 3 possible outcomes, hence our denominator was 3. That's why this is the way it is. Any questions there? Because this is something that like wasn't super intuitive to me when I was in school, so I've just wanted to make sure that's highlighted accurately there, because it makes a lot more intuitive sense as to what we're actually supposed to be doing with it. But okay, the main skill is going to be actually using that formula there and interpreting the results. So in this case, we're looking at probability of x being greater than or equal to 1, given that x is less than 3. So first thing we'd want to do is set up that probability equation. Oh, excuse me. I pretty much always will stick with this at the very beginning. Yes, you could hypothetically imagine it in your head to say, okay, I need the intersection of these two things, and I need the conditional itself. Just write it out. It won't kill you. And from here, what I like to do, at least in the context of something like discrete, is draw out number lines. So, for instance, drawing out the two outcomes, x greater than or equal to 1, is this bit here. Right, we've got our numbers 0, 1, 2, 3, so that's why this caps out at 3 here. This is 1, 2, 3. And then the other outcome was x less than 3. That's going to be all of these, excluding 3. Right, we cap out at 2 because this is non-inclusive on 3. So we now have each of the individual outcomes. That's already gotten us our denominator. Probability x less than 3 is that thing there. The intersection is therefore where these two things overlap on your number line. It's a nice visual to represent, or to figure out what you're actually trying to do here. Again, as you do these more and more and more, you might not need to use a number line here, but depending on how complicated the scenario is, sometimes even I will draw out these things just to get an idea of what I'm actually looking at and make sure, quick sanity check, that I'm actually using the right numbers here. So if the intersection is therefore between 1 and 2 inclusive, then that means my intersection is going to be the addition of these two numbers, x equals 1, x equals 2. That's why those appear there. In fact, you can even see I've done a little half step there by simplifying the nasty looking intersection symbol into something a bit more practical to visualize a bit better. So yeah, adding those up, and then the other thing was x less than 3, which means all of these numbers. Two ways you can go about it. One is to just add all three of these numbers together. The other is to use complement probabilities like we saw before. This is everything except for x equals 3, and so yeah. So for that reason, you can do 1 minus on this instead. Two ways of going about it. If you're doing tech free, you might be adding like this. If you're doing tech active, you might just do a 1 minus because it's slightly quicker to write out. And that gives you your conditional. Again, further validate that your probabilities do in fact belong between 0 and 1 at the end. Not sure I understood the example? Sure, that's fine. Okay, so from the top, the notation here is implying that we are doing conditional probability. That's what this pipe symbol means. The thing to the left is the outcome we're looking for. The thing to the right is the conditional itself, which is why the denominator of our probability that we're trying to solve is the thing on the right, the conditional. On the top is the intersection. Again, that's just being borrowed from this formula here. Intersection of the two events on top, probability of the outcome that is conditional on the bottom. From here, I like to do a visual. So I essentially get out my number line and I draw out what those look like, because sometimes it can be a bit complicated to figure out what your intersection actually is. Your intersection is just where do the two inequalities overlap. So if you do, for instance, the x less than 3, you're going to have your numbers between 0, 1, and 2, because you're non-inclusive of the 3, which is why you draw your number line as follows. From there, x greater than or equal to 1, that just means the inclusive of 1, and then capping out at the top of the table, 3. That's why our number line goes from, on the bottom, 1, 2, 3. The intersection is just therefore where those two things overlap. which is why we're able to replace this nastier equation by just saying, okay, it's between 1 and 2. Is that alright so far? Fully get it from here? Yeah, okay, sick. And then yeah, from there it's just using the table to add everything up and simplify. That's discrete. So that's how we use our probability tables, and yeah, that's pretty much what discrete will look like a lot. The other aspect of discrete is going to be the statistics themselves. So I'll just do a quick pulse check here. How are we doing? Do we want to practice some of the concepts that were discussed in here, or are we good to keep going with theory, lecture? Move on. Okay. Awesome. So, mean, variance, and standard deviation. You'll see these a lot. These are the key statistics that you'll have to solve for literally all of the probability types. If we do a quick overview of those, you've got discrete, binomial, continuous, normal, sampling and estimation. All of these will use those statistics. What's it all about? Well, they are calculated a little bit differently depending on what probability type you are trying to solve. In the context of discrete, the most succinct way to describe the mean mathematically is using this nasty symbol. That's just there for your interest. In reality, what you're essentially doing here is taking your outcome value, multiplying it by the corresponding probability, doing that for each individual pair, and then adding all the results together. That's functionally what you're doing here. This is how you calculate the mean, or otherwise referred to as the expected value. You're effectively finding the weighted average of your data set. That's how this is expressed. The sum notation, you sum from your first element all the way to your last element. The multiplication of the outcome and its corresponding probability. So in this case, it is x0 probability 0, which is these two, right? 0 times 0.216 plus 1 times 0.432 plus 2 times 0.288. Keep going until you end at the end of the table. What's the difference between this mean and the simple mean of adding values and dividing by a number of results? Yeah, cool, that's a good question. So the difference is what I was referring to here, which is you're effectively doing a weighted average value, where you are considering that certain outcomes have different weightings attached to them, the number that's actually output by it, and you are weighting your average according to that. Yeah, what you're really doing here is finding what's referred to as the weighted average. What you're describing by just figuring out the number of outcomes and dividing by total number of outcomes, that is the more accurate. That's the actual mean. What we're doing here is weighted average, and that's what's expected of you in the actual thing. Yeah, no, that's totally fine. Cool. So yeah, your weighted average is therefore 1.2. It's useful for things like gambling games or stuff like that, where you want to know what your average is going to be over a certain duration of time. Like for instance, if this is like number of dollars earned on your gambling game, you earn 0, you earn 1, you earn 2 or 3. For 1, play that game forever, because that's insane, you never lose money. But 2, you can then calculate that, okay, if I do this infinitely, every time I roll, I'm basically adding $1.2 to my bank account, which would be pretty sick. It also is worth highlighting that, worth doing a quick sanity check once again. Because you're doing so many little individual calculations here, it's likely that you might misinput something. And so just quickly have a look and be like, okay, is my mean, my weighted average, actually centered where I expect it to? If we look at all the probability outcomes here, the highest likelihood outcome is probability x equals 1. From there, if you look either side of it, the probability is weighted a little bit to the right. You can see how 0.216 is a bit smaller than 0.288. So you'll have a peak in the middle here, but you'll then drift off more on the right-hand side than you would the left-hand side. So the fact that it's 1.2 seems about right, because you're starting at your most likely outcome and then, yeah, drifting over a little bit. A good way of thinking about this is like a heat map of values. Yeah, precisely. In fact, I can kind of show you a little bit of that. Let me, oh geez, I clicked the wrong button and now I'm everywhere. Let's pull this up. You do get to explore a bit of this in the very last chapter, actually, where what you'll find is, in the real world, a lot of your outcomes are what's referred to as normally distributed. And this is kind of like, I think, what you were exploring there, which is like your heat map of values. If you run the outcome, the experiment multiple times, you'll see that one of the outcomes is more likely than the other, so on and so forth, and you'll see that you approximately get this little bell curve looking thing going on for most things. But this is like right at the end. But okay, that's what's going on here. There's nothing too crazy to discuss. It's just adding and multiplying over and over again. It's just annoying to do. Yeah, okay, let's do it. So the stuff that's talked about here is pretty much textbook exclusive and perhaps SAC exclusive. I've never seen this matter in an exam except for a very special condition, which you basically don't even think of as doing this. So we'll touch it anyway, just because it might show up in your SAC, and it definitely makes an appearance in the actual textbook. So if you have to do it for homework, you'll at least have something to follow up on. Just note that you don't really need this for the exam. What we were doing before was finding E of x, the expected value. What we're looking at here is what happens if you like apply a transformation to your expected value, like you're further weighting it in a certain way. Why would you do this? Great question. It's used in calculating some other statistic that we'll have a look at later, but that's pretty much all I got for like why you would do this. As for how you do it, you basically treat this as exactly what it says. Whatever the x value is, you're going to multiply that x value by 2 and add 3 to it before you multiply it with the probability. So beforehand we were usually taking the outcome and then multiplying it by the probability directly. In this case we are now multiplying it by 2, adding 3, and then multiplying 0.2. That's what this says here. 2 times the 0, add 3, and then multiply that by 0.2. So on and so forth for the rest of them. The one that matters the most is going to be the e of x squared one, where you are squaring the result. Again, it's x squared. So you take the x value, square it, and then multiply by the probability. 0 squared is 0, times 0.2 gets you 0. 1 squared is 1, times 0.15, 0.15. 2 squared is 4, times 0.6, 3 squared is 9, times 0.05. That gets used in the calculation of what's referred to as the variance, which is a measure of spread, how spread out your data set is. So as an example, if you had, actually maybe I have them, yeah, as an example here, this would be considered to have low spread. And the reason why is because a decent chunk of the probability is centered on a specific value, x equals 2, has a probability of 60%. A table that has high spread might be one that has 0.25 across the board, 25% chance here, 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 here. They are spread out as evenly as physically possible. That would be a high variance, high spread distribution. As for calculating it, you need to know these two outcomes, basically. You need to do your e of x squared, which we discussed earlier, was just squaring each of these numbers before you multiply it with the thing. And then you need your e of x all squared. So make particular note of the use of brackets here. This means find your regular e of x and then square the result. So if we look at that, e of x squared, if we use the result from earlier, we figured out it was 1.5. You square the mean that you calculated earlier, giving you 9 on 4. Then from there, you just do the variance equation itself. Take this one, subtract this one. This can be pretty nasty. There's technically another way of doing it. I'm glossing over it for a reason, because if you look at the amount of math that's involved in doing it in one line, versus excuse me, versus if you do it in 2 separate lines and then add at the end, one is significantly easier to follow. So if you want, you can read up on what's going on here. It is a valid way of doing it. My preference or my recommendation would be do it in 2 parts. Find this one, then find that one, then perform your subtraction. We're not even going to touch on this because even the textbook doesn't really like touching on it. Just like how you can put functions on, like transformations on your expected value, you can put it on the variance as well. It's just so not worth discussing. But it's there in case you guys really, for some reason, need it on your SAC or mainly a textbook. Lastly is the standard deviation. So standard deviation, by definition, is always the square root of variance. So no matter what way you're calculating your mean, your variance, depending on what probability type you're using, finding the standard deviation in all probability types is just a matter of finding the variance and square rooting it. Why do we do this? Well, I can give you a bit of an idea. If you think about what a square root does to a number, it essentially normalizes or standardizes how your spread is being represented. Is that the little symbol for standard deviation? That one here, yeah. So this one is the Greek letter sigma. That is how standard deviation is expressed, which is why if you have a look at where is it? The equation for variance, it's sigma squared, right? Standard deviation squared. Because if you square root to get variance, you should square to get back to. Wait, sorry, other way around. If you square root to get standard deviation, you should square to get back to variance. So yeah, that symbol there is your standard deviation, correct? Yeah, and as for like why do you look at standard deviations rather than variance? There's a couple of reasons. One is that it brings all the numbers closer together, so it's easier to normalize what you're looking at. For instance, if you have like 2 varying quantities, like for instance, actually you do this in your grades for your different SAC scores, right? And how VCAR will compare them and get you an ATAR at the end of the day. You know, you'll have different different raw numbers that you get for each of your results for different subjects, but because they all need to be compared together, there is a certain way you can convert them into a standard spread or a standard deviation. And we'll look more about how that's explored in normal distribution. But for now, that's sort of why this exists. But yeah, there's nothing really to talk about beyond that. If you know how to calculate variance, you now know how to calculate standard deviation. You just square root. Last up are the confidence intervals. So this is a bit, again, like I was discussing with your SAC grades and your exam grades, how they all get sort of normalized against each other to compare. There is such thing as a confidence interval, and the way it works is the number that's represented at the beginning is the percent likelihood that your result falls within some boundary. So for instance, a 95% confidence interval would be like me saying, I'm 95% confident that your results are going to be between somewhere between 10% and 90% in an exam, let's say. The numbers that I mention as the upper and lower bound will be different depending on what this calculation is. And the way you do it depends on the confidence interval you are trying to calculate. 95% is the one that's most common, and that will be where you find your mean, that's the Greek letter mu there, and you add and subtract 2 standard deviations to that value, and whatever that looks like becomes your upper and lower bound. For 68% confidence, you only want to do plus minus 1 standard deviation either side of your mean, and for 99%, you're plus minus 3 standard deviations. So they're not just arbitrarily stated, it's physically calculated using mean and standard deviation, depending on, in fact yours would be, yeah, this would be discrete, because you can only have certain percentage outcomes. So your SAC grades, your exam grades would be discrete and will be beholden to the same calculations of mean, standard deviation, variance that we're looking at literally right here. So how do we actually do what I've just been discussing? Well, if we look at the equation for it, we just need the mean and we need the standard deviation. We've already discussed how the mean is calculated. It's just multiplying each individual pairing and then adding the results. We've done this before, so I'm just going to copy the result. Variance was very similar. Again, we've done that before, so it's just the e of x squared, so squaring each of these before multiplying it, and then taking this result, squaring it. Furthermore, to get down to standard deviation, which is what we need, we're just going to square root whatever the variance was. Thus, our 95% confidence interval, we now need to do the mean plus 2 standard deviations and the mean minus 2 standard deviations. Sub in, simplify, simplify, and what you'll find is a strange result here. Excuse me. This is effectively saying that when we look at our outcomes 0 to 3, I'm saying I'm 95% likely that all of our outcomes are going to be between negative 0.23 and 3.23, which is obviously less than the 0 and more than the 3. So what the hell have we done here? Is this an error? It's not an error necessarily, it's just a misapplied use of this statistic. This is something in the real world you would do when you have a lot more outcomes than just 4. You will find that as the number of outcomes increases, doing a 95% confidence interval for those outcomes is significantly more useful. So that's just to say, if you do have to do it on these smaller data sets, it's because your teacher has maybe not necessarily considered that you shouldn't be doing it on smaller data sets. This doesn't appear in the textbook. You won't get numbers that are this stupid. The only reason it's in here is because I had a student once, like the very beginning of my career, who had worksheets that had small sets like this, and you were getting really weird results for your 95% confidence interval, but they are correct, because it's just a limitation of the data set rather than a limitation of our ability to calculate. Cool. Okay. That's all the statistics for discrete. Mean, variance, standard deviation, and then an application of it. Does the leftover 1% go on forever if the data range were larger? Yeah, so if we go all the way up to like 99% confidence interval, you're doing plus minus 3 standard deviations. These are just the ones that are explicitly taught in methods. Yes, you're essentially right where you'll never get 100% confidence interval, or more realistically, it's kind of useless to think of a 100% confidence interval because it's just, cool, my data set starts here, it ends here, that's my 100% confidence interval. So it's kind of useless to think about it in that way, because you just look at the end and the beginning. But yes, you basically will asymptotically approach 100% and never actually reach it, depending on your data set. In discrete, there is obviously a limit, but in continuous, which is what we look at after discrete, let me get the normal distribution up. Standard normal. You will see that you asymptotically approach probability 0. Just for a bit of context, probability is given as area under the curve. So you can see that it asymptotically approaches there. In fact, do I have the equation? Because that'll actually help explore it a bit. Yeah, here you go. So that right there is the equation of the normal distribution. And if you look at it, it's an exponential. It's an exponential that is decaying, and it's got a squared term in there, which is why you both decay on the right and decay on the left. But if we know anything about how exponentials work, they asymptotically approach a value, never actually reach it. So yeah, it'll go on forever, effectively. Why 68% confidence interval? Just an example. These are just the 3 standard ones that VCAR wants you to know about. It also makes an appearance right here. Yeah, so you can see plus minus 1 standard deviation is roughly 68% of the results. Plus minus 2 standard deviations, if you add all these up, is going to be roughly 0.95. And again, plus minus 3, plus minus 4, plus minus 5. It does go on forever, but the ones you look at in methods is pretty much exclusively 95%, but it is expected that you understand the plus minus 1 and plus minus 2 standard deviations. So it's not really just an example, it's just that that's what it is when you do plus minus 1 standard deviation centered from your mean. And you can see it's not quite 68, it's again just an approximate. Right? If you add these up, you get 68 and a bit more. Cool. Okay. Probably a bit too late to do any meaningful practice on these things. So maybe if you'll bear with me the next 4 minutes or so, I'll just introduce binomial. We've already done a lecture for the full hour, might as well finish it up with more. Excuse me. Okay, so what is binomial? You can think of binomial as a subset of discrete probability. So everything that we discuss in this chapter section, everything that applies to discrete also applies here. With binomial specifically, there are further rules that you can use that simplify what you're doing. What is a binomial distribution? The key is kind of in the name there. Binomial, binome, 2 possible outcomes, binary system, zeros and ones, that sort of thing. So essentially, if you have only 2 possible outcomes for a given scenario, heads or tails, that sort of thing, then you're likely to have binomial. There are further restrictions on it. You need to have independent trials. So basically, every time you toss that coin, the coin should not get damaged from toss to toss and therefore weight the probabilities differently or whatever. You want to maintain a 50-50 split every single time you do your 2 outcomes. That's not necessarily to say that all binomial is 50-50, just means that the probabilities cannot change. Like for instance, if it's 30-70, you can't then make it 40-60 through, or it can't then go to 40-60. There's a few keywords here that I've discussed just so you can understand like when you're likely to have binomial or not. Keywords like replaced or returned, that's what we were talking about earlier, where you're drawing balls out of a jar and you're putting it back every single time. Thus the probabilities aren't changing. Keywords like independent, right? That's a criteria. This is the notation itself for binomial. You got the standard, you got the discrete random variable. You got bi for binomial, and the 2 binomial parameters: n, the number of times you're repeating the experiment, and p, the probability of getting a success, desired outcome. There is a calculation for it. It looks like hell. It's not too bad. You just got to remember what factorials are. Does anyone need a refresher on how factorials work, by the way? It's essentially just a repeated multiplication. So if you have like 5 factorial, that's the same as 5 times 4 times 3 times 2 times 1, and you terminate at 1. So you'll see that you get a bunch of factorials. This is the NCR equation from those who have done counting methods before. You got the probability of success to the power of the number of successes you want, and you got the probability of a fail, 1 minus a success, times the number of fails that you want. So if you want to find the probability of tossing 4 heads at all, not necessarily 4 heads in a row, just 4 heads, you would therefore have x equals 4, n is 5. Right? N is 5 because it's the number of the times you're tossing the coin, x is 4 because it's 4 outcomes of heads, and your p-value is going to be 50% because it's 50-50 heads or tails. Plug it all in, simplify, and you'll find that these will end up simplifying quite nicely, down to just a little coefficient at the start, the probability of a success times the probability of the fails. In the case of 50-50, those combine even further, so you're even more lucky. But yeah. And on the CAS, you can just do this directly, right? This is in your menu 5, where is it? If I pull up the CAS, you'll see you'll have menu 5 for probability, 5 for distributions, and if you go down to A and B, you'll have the binomial PDF and CDF. What we just did there was the binomial PDF probability distribution function. Alright, I've just about lost my voice, but I am happy to clarify any further questions for a little bit longer if there are any. Otherwise, thank you for coming.
Thank you.
Cheers.
Thanks, Chris.
Yeah, no worries.
Thank you.
Thank you.
Hey, could you explain that last part again?
The
It
part of the
completely stuck
equation.
with me. Yeah.
Yeah,
The
sure.
Bernoulli sequence.
Yeah. So the Bernoulli sequence here, this first part of the equation is essentially calculating the number of possible sequences of outcomes. So if you think about when we were doing the picking the balls out of the jar, we had like white, black, 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 white, black, 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 white.
Yeah.
Counting the number of ways you could order things. That's what this part of the equation is doing. It's calculating the number of ways you could order that sort of stuff. From here, this next term is essentially just how many successes do you want, because P is the probability of the success, the desired outcome. And then this one is effectively just the number of fails you want. 1 minus P, if P is a success, then 1 minus P should be a fail. And N minus X is just, okay, you had X successes, so you have this leftover number of fails. That's what each of those terms do. As for how you pick out what's your N, what's your X, what's your P, the N is the number of trials, so the number of times you do the thing. If you're tossing it 5 times in a row, you have N equals 5. The P value is the probability of your success, so if it's saying probability of 4 heads, you choose heads as your success. In the coin toss example, it doesn't really matter if you choose heads or tails for your success, because they're both 50-50, of course, but in a lot of other examples it will matter. And lastly is the X value, which is basically the number of successes you want, which in this case is 4. You want to toss 4 heads. So you plug them all in, simplify down, and whatever you get is whatever you get there. Is that cool enough?
I think I got it.
I think. Okay. Was the issue about the simplification or where the terms are coming from?
I guess it's where the terms are coming from.
Where the terms are coming from? Yeah. So N, number of times you repeat the experiment. P, probability of success. X, number of successes. Those are the only
Okay.
3 variables that are in here.
Oh,
N,
okay.
trials. P, probability. And X is the number of outcomes you want.
Alright.
Cool.
Okay.
Yeah, give them a shot. Just keep practicing in the textbook itself, and you'll get your head around it pretty quickly, I'm sure.
Okay.
Easy.
Alright.
Um,
Thanks.
Yeah, no worries. And this will be
Have a good
helpful for, how we're doing like the black, white, white thing. Because those weren't changing, you would now do like probability of success was 4 out of 10. So you could actually use binomial to solve that previous question, because it was either white or black, 2 outcomes. And because you're replacing it every single time, it's now properly binomial. You're not changing probabilities. So you can see how this now backdates to help you out with previous questions.
Yep.
But cool. Okay, I'll leave you to it. If you have any questions, of course, feel free to submit them. Otherwise,
Yep.
thanks for coming.
Yeah. Thanks. Have a good day.
You too.